In this slidecast, we'll talk about the software lifecycle. Now, the purpose of a typical programming assignment in an introductory course such as ours is quite different than the purpose that software is developed in industry. For this course, the intent is for you to learn a particular programming assignment, and you'll work on it on your own, and perhaps you and the TA may be the only ones who ever see it. Now, in industry, products are developed in response to customer needs. They're usually used over an extended period of time, created by teams of people, and they require a systems analyst to work with a customer to understand what the need is and how to meet it. And software products go through several stages. We call this the software life cycle. Now, the waterfall model is a very simple model that's used to kind of explain this life cycle. And there are 5 activities, and the idea is that we go through each activity once, and the results of that activity flow into the next activity. Now, here are the 5 phases, the 5 activities in this waterfall model, and I think they're instructive for you to think about even as you do your programming assignments. So first we have requirements, where the requirements of the system are determined. Usually for your programming assignments, we have figured out the requirements and they're given to you. Now, an analysis phase is where we study and clarify the requirements and think about the overall architecture and the subsystems we're going to need to solve a problem. Once we've done a thorough enough analysis, we'll get to the point where we can actually design the classes when we're using an object-oriented language like C++. So we define the functions and the data fields we need. We think about the detailed algorithms that it will take to implement these functions. And finally, notice it isn't till activity 4 where we actually produce the code in C++ for our software system. Now, this is really, really significant. Even in the assignments we're going to do in this semester, I think you need to do some careful thought, develop some understanding, and design a solution before you start entering a solution. I often half-jokingly tell students that the Siemens law of software development for doing your programs in class is that the time it takes you to complete an assignment will be inversely proportional to how early you start typing in your code. And the point I'm trying to make to students is that you need to spend some time to understand the requirements and design a solution before you start entering your code. Many times when I see students get into difficulties completing an assignment, the root cause is that they don't understand something important about the problem they're trying to solve. So I think resist the temptation to immediately start coding. Now, for very small programs, there's a temptation to just start coding, and as you figure it out as you're coding it, it's easy to go back and make complete revisions when you have a very short program. But as you move through classes and start building larger and larger systems, then I think following this kind of planning and designing you will find to be very helpful and will save you time in the long run. Now, the final activity is testing, where we take each class and we test it in isolation. That's known as unit testing, and then we test classes together in integration testing to make sure they work correctly and they meet the requirements. Now, this waterfall model is very simple, but it's unworkable in practice. What it means is this isn't really how large software products are developed, because we don't go through just these simple 5 stages in a nice, neat order. In fact, the real world's a lot messier than this. We don't understand the requirements. We learn things as we go along. Maybe when you actually start implementing something, we find out we learn things that we didn't anticipate or didn't realize when we were designing. So there tends to be a lot of more feedback and cycling through these phases. So unified model is one example of someone's attempt to try to improve on the waterfall model and make something that's more realistic. And we divide the problem into cycles called phases and iterations. And the idea is at the end of each cycle, we review with the users and get feedback from them, which will feed into the next cycle. Now, here's a diagram of this process. So we still have the same 5 activities we had in the waterfall model. They're shown here. But this is illustrating, we divide up our cycles into phases. There's 4 phases, and then there's a number of iterations. And the idea is that time moves along in this direction. As we start in, let's say, the first iteration, we'll just be doing some requirements gathering, maybe just a tiny bit of analysis. And this analysis perhaps will give us some input back into our requirements. As we move through the phases, we spend more of our time doing requirements early on, but we start ramping up our analysis kind of at the same time. As we learn more about our problem, then we start doing our more detailed design. And finally, notice the implementation, comes here mostly during the construction phase of the project. But even during the early parts of implementation, that might feed useful information back into the analysis and the requirements phases. Also notice that our system, we can start doing some testing, maybe unit testing or other testing early on, and then maybe the bulk of our testing is towards the latter part of the project. So I think this diagram does a much nicer job of illustrating, what takes place on a large software project, particularly one that involves multiple people. So here are the life cycle activities, and this is similar to what we saw before. We have requirements. Here we have the design broken into an architecture design, a component design, and a detailed design. Then we get to implementation. We have our various kinds of testing. Then a product could be installed or it could be released. And then we go through a maintenance phase where we enhance the product, and make corrections when we find bugs. Now, the requirement specification, it usually results in a written description of the requirements. And in practice, it requires extensive interaction between the users or the customers and the people who are building the system. Now, let's illustrate sort of the problem that can happen during the requirements phase. So here's a problem statement. It's based on a telephone directory program. This is sort of a running example that we're going to see throughout Chapter 1. So the problem statement is to write an interactive telephone directory program. It will contain a collection of names and telephone numbers. We should be able to insert entries into the directory, retrieve an entry, and change or update an entry. Now, from that problem statement, next we see here are a number of questions that come out of that problem statement, because we're going to see that there were some important details that are missing. Let's look at some examples. So, is there an initial list of names and numbers to be stored in the directory beforehand, or are all the entries inserted at runtime? And if there is an initial list, does it start out in a file, or does the user enter it interactively? We go on with, here's some other questions that will come up. If you'd like to, you can pause this slidecast and take some time to read through this, but the important point is that initial problem statement didn't produce, or didn't answer all the questions. As you start thinking more deeply about this software product, then during analysis you can think of some unanswered questions. Now, this is the kind of thing in class we may give you a programming lab and give you an assignment, but as you start thinking about it, maybe you're going to think of some alternatives or choices that aren't specified, and perhaps you'll have to ask us about that if you think that makes a difference. And in some cases, you could choose. You'll be able to choose alternatives, or you may feel we need to select that alternative and give you some direction ahead of time. So before the analysis stage begins, you should have a complete understanding of the problem statement. And during analysis, we can think of different approaches in the way that we might build our solution. So I think this second bullet point is very important. So you can have a specification of what someone wants, but thinking carefully about different alternatives can be very helpful, because the first thing you think of may be an alternative that has some weaknesses, and spending more time, you might be able to come up with a better alternative. So even in this class, you may not want to jump and immediately start building the first idea that comes to your mind. Be thoughtful and think about, as you identify some pros and cons, and see if you can think of some other alternatives that may have important advantages. So here's some things you might consider during an analysis stage. Is there already existing software that could solve part of the requirements? Or do we need to develop something entirely new? Do we need some new hardware or software? Once you have some options, what are the costs and benefits of each? So you should do this kind of thinking when you approach your programming assignments. Now, sometimes in a class assignment, you may not have some flexibility because we may give you some requirements and dictate a particular solution because there's something important you need to learn from that particular solution. So in this course, you can carefully think about the input-output requirements of the system. You can consider any interaction with the user. But the idea is you want to break up your system into a set of small, manageable components. So if we ask you to do, you're going to get slightly bigger programs than you saw in 142. And thinking carefully and break it up into parts is going to help you manage the complexity, and you can deal with sort of one part at a time. So you should be able to take any of our labs this semester and break them down into smaller sub-problems that you can manage. Now, top-down design, also known as stepwise refinement, is the process of starting at the top level with some original problem and dividing it into subproblems. And then every subproblem identifies a subsystem for solving that problem. So in our telephone directory program, we can let that problem statement represent a level 0, and then we can break that down into some 4 subproblems. Maybe reading the initial directory, inserting a new entry in the directory, editing an entry, and retrieving and displaying an entry. And then that level 1 subproblem of reading an initial directory, we can further break that down into 2 subproblems: to read an entry from a file and store an entry in the directory. And here's another level 1 subproblem that we can break down into another level 2 of subproblems. Okay, read a name from the user, find a name in the directory, get the entry information from the directory, and display it to an end user. Okay, another kind of design is known as object-oriented design. It focuses on data elements and the operations together. So in object-oriented design, we identify the objects that participate in our problem, we identify how these objects interact, and we model this interaction as messages. And usually for every class, we provide an operator or a member function to process messages. Now here's an important suggestion. You can look at the nouns in a problem statement to help identify objects, and verbs often indicate operators. So that means the nouns in the problem statement can often be modeled as classes, C++ classes, and the verbs are the actions, and you'll have methods on your classes to support those. So for a lot of students, maybe starting out a program, if we don't give you maybe some class definitions, then sometimes this can be a little difficulty just knowing where to begin, sort of when you have a blank slate. And I think this suggestion here is often going to be your solution, is to look at the statement and think about the nouns and verbs. So if we look at this phone directory problem, we can see that we need a directory, we need entries in the directory. Entries have a name and a number, and we have a file that contains the entries. Okay, there's a user involved who's external to the problem, and the user selects the operations to perform. So object-oriented design incorporates some ideas from top-down design. The top-down design, in that process, we can determine some of the nouns, and some of these sub-problems will correspond exactly to some of the operations. But it also has some elements of what's known as bottom-up design, and that focuses on the design of individual system components. So object-oriented design has both top-down and bottom-up design. Now, Unified Modeling Language, or UML, is a tool where we can create diagrams to illustrate the interaction between classes and between classes and the external entities, such as users. And these diagrams, there's a standard way of creating these to document these relationships and this is standard and known across the industry. So your textbook will have some examples of UML, and you should use UML diagrams to describe the classes that you're going to develop in your programming assignments. And if you learn about UML, you may encounter this in industry, and you'll be sort of prepared to understand sort of the documentation that others are producing. So we're going to see examples throughout the textbook, and Appendix B is devoted to UML. So you can go take a look at Appendix B to get a clear idea of the different kinds of things that UML can be used for. Now here's an example of a UML diagram. And it represents the user and then the different entities, the different objects, the directory, an entry in the directory, and the file that contains all the entries. And these lines connecting, arrows and lines represent the interactions between these entities. Users send commands to the directory. The directory contains an entry. The directory reads from and writes to the file, and the file contains an entry. So this is a way of representing the entities in the system and the interactions that occur. And that brings us to the end of our Slidecast.